All right, so when we're talking about what's coming up today for the test, we know this unit is called covalent compounds and covalent bonding, but I want you to remember that since we've studied ionic bonding, we're going to continue that. And you need to remember that electrons are transferred from a metal to a non-metal. That ionic bonds form when electronegativity differences between atoms is greater than 1.7. Specifically, we're talking about between a metal and a non-metal. We're usually talking about group 1 or 2 metals. These are formula units. They're not molecules. You need to understand why. Remember that these ions that form, the metals that have lost electrons become cations. The nonmetals that have gained electrons become anions, and they stick together and they form a crystal lattice. They are a formula unit, the lowest whole number ratio. You definitely need to know how to name and formula right for ionic compounds and acids. So you're going to have to review that from your last unit. Make sure you know how to do that. Covalent bonding, same thing. This is two nonmetals. Covalent share. So remember, co, together, so sharing. Literally it tells you sharing valence electrons. Just like we write cohabitat for sharing a habitat or sharing a house. We're talking about sharing valence electrons. So covalent, sharing valent. Okay? How are these properties different? So you need to be sure and review that. Understand the octet rule. Understand that hydrogen and beryllium and boron are exceptions. And also you need to understand those that can handle expanded octets. For example, sulfur and phosphorus. Lewis structures, you've got to know how to draw these. We've practiced lots and lots of these in class. We'll do a few more here in a few minutes, but you've got to know how to handle those. Understand molecular polarity. I'm going to ask the two questions. Are there any lone pairs in the central atom? If yes, that's going to be a polar atom. There are different types of atoms around the center. If yes, that's going to be a polar atom, a polar molecule, pardon me. Nonpolar means that there's an equal sharing of electron and it's symmetrical. So that helps me to remember what nonpolar means. Bond polarity, if they're totally equal, and we practice this in our collisions work as well, if it's totally equal, like the fluorine-fluorine bond in our collisions, or HH here, the electrons are going to be around this hydrogen or this hydrogen equally. If it's a polar covalent bond, like this, carbon and fluorine, fluorine is much more electronegative. The electrons are going to spend much more of their time around fluorine. And again, we had an example of that in our collisions work. Extremely unequal sharing is the ionic bond. We have electronegativity differences much greater than 1.7. And in this case, fluorine is so electronegative and magnesium has such a low electronegativity that the two electrons would leave magnesium and go to fluorine. You need to know the name of the molecules, like carbon monoxide, carbon dioxide, water, ammonia, and methane. And if you remember in class, of course, I hope you all know water by now. I'm really only asking you to know ammonia and methane as special terms. Carbon monoxide and carbon dioxide, we can use our naming rules to come up with that. Finally, we need to talk about VSEPR, valence, shell, electron, pair, repulsion. This is what makes these molecular shapes happen. Okay? That's what the acronym stands for. You need to be able to identify the shapes. You need to be able to think about sigma and pi bonds, understand bond length and bond strength. In other words, a double is stronger than a single, and a triple is stronger and shorter than a double here. We're going to skip hybridization. All right. Intermolecular forces. These are the three different types that you're going to have to know for this exam. I know we talked about a few others in class, and that's fine. You definitely need to know those. We're really going to hit you hard on the test. London dispersion. That's only nonpolar. Okay, if something is nonpolar, it only has limited dispersion. This is dipole-dipole, so this is polar, and this is polar with a hydrogen bonded to F, O, or N. Okay, remember these hydrogens that want to have fun. This is polar molecule with one of these things is going to have hydrogen bonding. All right, let's go ahead and take a look at some of our exercises and see how that goes. Lewis dot structures. Let's talk about this. How many valence electrons do each of these following groups have? The halogens. The halogens have 7, and I could draw that. An example of a halogen would be chlorine. 1, 2, 3, 4, 5, 6, 7. Alkali metals. Alkali metals have 1 valence electron, and an example of that might be sodium. Okay? Alkaline earth metals. Alkaline earth metals have 2. An example of that might be magnesium. 1, 2. Noble gases. Noble gas, everybody but helium, because helium only has 2. So I'm going to go ahead and do helium for you. Helium has our 2. Everybody else, like neon, has 1, 2, 3, 4, 5, 6, 7, 8. Okay? Alright. Ionic and covalent naming. These are going to be mixed all over the test. By now, I expect you to be able to recognize something, whether it's ionic or covalent, and that's very important. You're going to have to be able to do that before you can actually name it. Because if it's ionic, it needs to use the ionic rules. And if it's covalent, it needs to use the covalent rules. So let's take a look here. MgCl2. I noticed that Mg is a metal, specifically an alkali metal. It's got a +2 alkaline earth metal. Excuse me, that's an alkaline earth metal. It has a +2 charge all the time. It's in group 2. It does not need a Roman numeral. So I'm just going to write magnesium chloride. Fantastic. CO3. Now I want you to pay careful attention here, because in the ionic world we might have called this something else. But notice it does not have a charge here. It does not have a charge here, so it's not the ion that some of y'all are thinking about. This would be named carbon trioxide. Okay? Let's look at this one, N2O5. Nitrogen is a nonmetal. Oxygen is a nonmetal. This is a covalent compound. This is dinitrogen pentoxide. Yes, and I did notice that on the page before. You have to know all these prefixes. You've got to know the di, tri, tetra, pent, hexa, hepta, right? All of those. Octa, you should know that. Nona, and finally deca. You need to know those. AlCl3 is aluminum. Aluminum chloride. Aluminum is a metal, right? Cl is a nonmetal, chlorine. So that's a metal and nonmetal. We're going to call that aluminum chloride. Aluminum always has a +3 charge. Therefore, I do not need a Roman numeral. HBr. Notice it starts with an H. It does not have a charge. I want to be very careful and recognize that this is an acid. A lot of y'all missed that on the test. This is an acid, and it's a binary acid because the only thing that's there is a hydrogen and the element itself. So this is hydrobromic acid. All right, let's take a look at number 6, H3PO4. Again, this starts with an H, doesn't have a charge. This is going to give you a big clue. This is an acid. And PO4, but this is an oxyacid, right? This is an oxyanion. So PO4, I'm going to write it up here, is, maybe I'll write it over here for you. This is phosphate. Let's do that for you. Phosphate. And if you remember, I ate too much and now I feel icky. So this is phosphoric and then I have to put its acid because it's H3. So this is phosphoric acid. Okay, remember we learned that from ionic. Fe2O3. Now this one's interesting because this is Fe is iron. It's going to be element 26. This one needs a Roman numeral because it's not in group 1, it's not in group 2, and it's not in the staircase. So we need to figure out how, what number that's going to be. And so if you remember the trick we used, we did a little here, and I'm going to kind of do the work over. Let's just do this on a little separate page here. So Fe2O3, is that right? Yep. Remember here. And yes, I know some of y'all learn how to reverse crisscross, and yes, that works quite a bit of the time, and sometimes it doesn't. So I have 3 oxygens. Each one has a -2 charge. So my total charge on the anion side is -6. That means on the cation side it has to be +6. And I happen to have 2 atoms of iron here, so +6 divided by 2 equals +3. Therefore, I'm going to write this as iron 1, 2, 3 oxide. That's where that comes from. That's what that means. I'm going to do this. This is iron 1, 2, 3 oxide. P6O7. P is a nonmetal. O is a nonmetal. 2 nonmetals makes it covalent. So this is hexaphosphorus heptoxide. So next we have CO. So nonmetal, nonmetal. I have 1 of each. Carbon monoxide. FeO. Fe is a metal, and once again, just like we had over here, it definitely needs a Roman numeral. Notice this is a different formula. So I'm going to go ahead and try this again, except this time I'm going to put FeO. I have 1 oxygen, -2, so that's a -2 on this side. This means I need a +2 on this side because these things have to equal 0. See, there's no 0 up there. There's only 1 Fe, so +2 divided by 1 is +2. This is iron 2 oxide. Again, that's where that comes from. So we'll go back up here. Iron 2 oxide. Alright, well now let's take a look at formula writing. So, if it is covalent, it's real easy. All I have to do is take my prefixes and add them up. So diphosphorus trioxide. If it's starting with a prefix, one of the number prefixes, right, that clues me right in that what we're talking about is a covalent. So diphosphorus, so this is P2 trioxide O3. And remember, for covalent compounds, we do not simplify. That's just the way it's written. Barium chlorate. Now what do I know about barium? Well, barium is a metal, and we got to find out what the charge on barium is. So we look at our periodic table, and we notice that barium is Ba, and it's +2, and chlorate, remember we've all memorized our polyatomic ions, chlorate is ClO3 -1. And I'm telling you guys, you've got to do this, at least for now. Maybe a little later you don't have to, but right now I need you to do this. You're going to take the 2 and the 1, and you're going to crisscross. Okay? So that's going to be Ba ClO3 2. Cobalt 3 sulfide, and yes, we should have parentheses here. Cobalt, remember what this 3 tells me? This 3 tells me that cobalt has a +3. So I've got CO +3, sulfide. I look at the periodic table, and I look at sulfur, and I notice that it has 2 steps. I need to add 2 electrons for it to become like a noble gas. So that's going to be -2. And again, I'm going to crisscross. I'm going to take this, bring this over here, and this is CO2S3. I have pentasulfur tribromide. So this is sulfur, bromide, this is S5Br3. That's the tri. Hydrofluoric acid. And yes, hopefully y'all are screaming right now that that is misspelled. It indeed is misspelled. It is not hydrofluoric acid, it's hydrofluoric acid. So fix that. The hydro tells me there's one H, or that tells me that it starts with an H, and fluoric, so this is -1, this is +1, I crisscross. Hydrofluoric acid formula is HF. The hydro here, the hydro tells me that it's only hydrogen and one other element. Let's compare that to phosphorus acid. Notice there's no hydro. There is an acid, so that tells me that it's got to have an H. Well, let's remind ourselves about that. So phosphorus acid, that, remember we say Sprite is delicious, and so that OUS turns into ITE. This is phosphite, okay? And the formula for phosphite, we remember because we have it memorized, and if you don't, you need to get that done. Phosphite is PO3 with a charge of -3. I know it's an acid, so I'm going to put an H +1, and just like we've done with all of our other compounds, this +1 goes over here, this 3 goes over here, and that makes it H3PO3. Okay? So H3PO3. Let's take a look at dihydrogen dioxide. You will probably recognize this as something else in just a moment, but let's go ahead and name it. So dihydrogen means I have 2 hydrogens, H2. Dioxide means I have 2 oxygens, H2O2. That's also known as hydrogen peroxide. All right. Iron 2 oxide. Well, we just happen to have it right up there, and it's the same thing. I've got Fe +2, O -2. I crisscross those two, and I reduce that to the lowest whole number ratio, and so that is FeO. Magnesium oxide is going to be very similar. Notice there's no Roman numeral because magnesium is always +2. Oxygen is always -2. I crisscross those. I can get Mg2O2, but then of course that reduces to the lowest whole number ratio, MgO. Cesium phosphide. So that is Cs +1. Phosphide is P -3. I crisscross those. I notice that cesium is a metal, and so that is CS3P. Okay, the bond between 2 nonmetals, that's covalent. In this type of bond, electrons are shared. Their particles are called molecules. Ionic bonds are formed between a metal and a nonmetal. In this type of bonds, electrons are transferred. Their particles are formula units. IMFs, London dispersion forces. So these are going to be weak, temporary attractions between non-polar molecules. Dipole-dipole, this is going to be stronger attractions between the positive and positive side of one molecule and negative side of another molecule. Hydrogen bonding is especially strong. Let's just put that S-T-R-O-N-G, strong. Dipole bond, when a molecule contains an H bonded to F, O, or N. Of course, I like to say when hydrogen wants to have fun. F, O, and N. An example of this might be H2O. Okay? Remember, H2O, water has hydrogen bonding.